Hello everyone and welcome to CSEN 601 Computer System Architecture. My name is Walid Al-Hifni and today I'm going to continue my overview series, and this time I will discuss the MIPS Datapath single cycle implementation. First of all, this video is not the practice assignment 7 solution, rather I will be explaining some important concepts while solving some exercises from the practice assignment, but not all. This video is divided into two parts. In part 1, I will explain the MIPS Datapath single cycle implementation, and then we will see the execution of an R format instruction passing through the different stages of the data path. In part 2, which will be the next video, we will see the execution of 3 I format instructions passing through the different data path stages, as well as solving exercises 2 and 3 from practice assignment 7. So, what is a data path? It can be seen as the hardware implementation of a certain processor, meaning after converting the instruction from assembly to machine code, where will this machine code run? It will run on your hardware. So the different connections between the buses and the multiple hardware elements like the registers, the arithmetic logic units, the adders, the multipliers, etc., they form the data path that the instruction will pass through to execute. Okay? In our simple implementation, MIPS is a single cycle implementation. What is the meaning of a single cycle implementation? It means that every instruction or each instruction takes only one clock cycle to get executed. So the cycles per instruction, or the CPI of our MIPS instruction set architecture or our MIPS instructions, is 1. All instructions in MIPS take one cycle or one clock cycle to get executed. Okay? So we have 5 different stages an instruction passes by in our simple implementation. We start with the instruction fetch stage, followed by the instruction decode and register file read stage, followed by the execute and address calculation stage, followed by the memory or mem stage, and finally the write back stage. So we have 5 stages. For an instruction to execute, it needs to pass through all of these 5 stages, and throughout this tutorial we will tackle how an instruction passes through all of these stages, and each stage performs or helps or contributes to the execution of an instruction. So let's start with the instruction fetch stage. In an instruction fetch, we have the instruction memory, which is one of the main or important components in our data path. In the instruction memory, as you can see my cursor, the program or our program resides in this memory, meaning that if I want to execute a program consisting of 5 instructions, all 5 instructions will be present in this instruction memory. But now we need to recall something important we talked about in the lectures and tutorials. We stated that MIPS is based on a von Neumann architecture, meaning that the instructions and data are both in the same physical memory. So we have one memory for instructions and data. Now, as your eyes can see, we have here an instruction memory and we have here a data memory. So why do we have two different memories in the data path, although we are based on the von Neumann architecture? The answer is very simple. Lecture 2, caches. The instruction memory acts as the instruction cache and the data memory acts as the data cache. So the instruction memory and the data memory are caches and are not the actual memory. At the end, the bottleneck, the instruction memory and the data memory, which are caches, are both connected to one physical main memory. But to provide a single cycle implementation, we divided our main memory into two caches, an instruction cache and a data cache. And if something is missing, the instruction cache or the data cache will retrieve it from the main memory and come back to the data path. Why did we perform this? Because, as I stated, we are a single cycle implementation, and in a single cycle implementation we can only access each component once per clock cycle. So in one clock cycle, every element in this data path can be only accessed once. It's like an edge triggered. It's accessed in the positive edge, for example, of the clock. So I cannot access the same component twice in one clock cycle. I need to wait for the next clock cycle if I want to access the same component again. For example, I can only access this instruction memory one time per clock cycle. So at clock cycle 1, I can only access it once. At clock cycle 2, I can only access it once, etc. Okay? So let's continue with our stages and the instruction fetch stage. As I stated, we have an instruction memory or an instruction cache that contains the program I want to execute. In the instruction fetch, I retrieve an instruction, meaning that I have here the PC, which is the program counter. It's a special register only accessed by the data path and hardware. And as a user, you cannot access this register. The program counter or PC contains the address of the next instruction. So I want to execute an instruction. I have its address in the program counter. So the program counter, the address present inside it, will tell me which instruction I want to retrieve from the instruction memory. And that's why we have here the program counter pointing to the instruction memory, telling me it's time to execute this instruction. So please retrieve this instruction with this address from the instruction memory. And as I stated, the address is present where? Is present at the or inside the PC. So the program counter or the PC contains the address of the next instruction to be executed. And now we will retrieve in the instruction fetch state the instruction I want to execute. How to get this instruction? I need to fetch it or get it or retrieve it from the instruction memory. And after getting this instruction, I need to update my program counter or PC so it can point to the next or the following instruction. And that's why we have here an adder, and I'm adding the current value of the program counter plus 4 and storing it back where? In the program counter. So I have here the program counter, it's an input to the adder. I have here plus 4 or 4, and then the result will follow this line and will be stored in the program counter. We will talk about the multiplexer later, but for now you need to understand the basic idea. I point to an instruction, I fetch this instruction, now I need to what? To update my program counter or PC to point to the next instruction. An important question, you should always know its answer because it's very tedious. Why do we increment the program counter by 4? Because as we stated before, our MIPS implementation is byte addressable, meaning all addresses are bytes. They are pointing to bytes. And as you can recall, in our implementation, one word equal 4 bytes. So since one word equal 4 bytes, to point to the next word, I need to do what? I need to increment by 4, since I point to bytes. So to skip byte 0, byte 1, byte 2, and byte 3 of word 0, so I can point to word 1, I need to do what? Byte 0 plus 4, so it will point to byte 4, which is the start of word 1. And as we stated, our instructions in MIPS are 32 bits, our data in MIPS is 32 bits, and the values inside the registers are what? Also 32 bits. And that's why a word in MIPS consists of 4 bytes, because 4 bytes are 32 bits. So that's why we increment by 4, because we are byte addressable. So to move from word 0 or from instruction 0 to instruction 1, I need to do what? Plus 4. So we finished the instruction fetch stage, which is getting the instruction I want to execute from the instruction memory. Then we move on to the second stage, which is the instruction decode and register file read. And the main component present in this stage is the register file. Okay, what is the register file? It contains all of our registers except the program counter, because the program counter is a separate register. But all of the other registers, like the saved registers S0, S1, etc., the T registers or the temporary registers T0, T1, etc., even the argument registers, the return value registers, all of these registers, all of our 32 registers are present inside this register file. So it's an important component, okay? Now let's see what occurs in this stage. What happens is, in the instruction decode stage, we get an instruction from the instruction memory. So the fetch stage gave us an instruction, and this instruction is passed to the instruction decode stage. In the instruction decode, I decode the instruction. What is the meaning of I decode the instruction? It means I will divide the instruction, the 32 bits instruction, into multiple fields. If you can recall the three instruction formats we discussed in class regarding the MIPS architecture, we stated that we have an R type and an I type and a J type. The R type is the register operations, the I type is the immediate and load and store operations, and finally the J type is for jumping. And as you can recall, we took the 32 bits instruction and divided it into multiple fields. For example, the R type instructions, we had an opcode, RS, RT, RD, shift amount, and function. And the I type, we got an opcode, RS, RT, and then immediate. And finally, the J type or the J format had an opcode and an address. So we were dividing the instruction into multiple fields. This is what occurs in the instruction decode. I divide my instruction into these fields specified in the instruction formats. But guess what? An important element you need to understand is that the data path is not smart enough. Meaning that in the instruction decode stage, the data path does not know which instruction it is executing. So it does not know whether this instruction is R format, I format, or J format. So what happens? You can guess it. What happens is that the instruction decode phase will divide this instruction to all possible combinations, to all possible formats. So it will try to decode this instruction as if it's an R type, as if it's an I type, and as if it's a J type. This image or this figure does not show the full data path. It is just a simple implementation, so not everything is appearing in this image or in this figure, but later on throughout this tutorial and the future tutorials, we will extend this data path to consider all different combinations and all different elements and divisions. So let's start. If it's an R-type instruction, how will it be decoded? We will have from bit 0 to bit 5 the function, from bit 6 to bit 10 the shift amount, from bit 11 to bit 15 the RD or the destination register, from bit 16 to bit 20 the RT or the source 2 register, and from bit 21 to bit 25 the RS or source 1 register, and finally from bit 26 to bit 31 is the opcode. All of these are represented, or all of these divisions are represented in the data path, but not on this figure. So in this figure, we can see what? We can see that this instruction from here can be divided into something called read register 1. Read register 1 can be considered bits from 21 to 25 of an instruction, which is the RS. Okay, and here we can have read register 2. So if I am an R format instruction, I will have read register 2, my second value will be stored in register RT, which is bits from 16 to what? To 20. So this line will contain bits from 16 to 20. And finally, the write register will be what? The RD or the destination register. So if I'm an R format, this will be bits from 11 to 15. Do not worry, the numbers will be present in the following examples. I'm just giving an overview. Okay, do not worry. So I'm dividing the instruction, for example, as if it is an R type. But guess what? I do not know whether this instruction is an R format, an I format, or a J format. So what happened here is the division of the three registers as if it's an R format. Guess what? If I'm an I format, how will I divide the instruction? I will have from bits 0 to 15 the immediate or offset, from 16 to 20 the RT, from 21 to 25 the RS, and from 26 to 31 the opcode. So the comments are the RS and the RT, but in the I type I have from 0 to 15 the immediate, whereas in the R type I had from 0 to 15 the function, the shift amount, and the destination or RD registers. So if I am an I-type format, I need to have or extract bits from 0 to 15 as a whole, not dividing it into 3 fields like the R type or the R format. So as you can see here, we can have a line coming from the instruction, which whereas it says I'm taking 16 bits, and this will take bits from 0 to 15, and it's taking copies of the bit. It's not extracting the bit and removing it from the original instruction. No, we are taking copies, because here, for example, the write register is from bits 11 to 15. Okay, and here the sign extend, the input to the sign extend module is taking bits from 0 to 15. So how come I have a common area? Because I'm taking copies. I'm not doing a cut operation. I'm not extracting and removing from the main instruction. No, I'm just taking a copy. That bits from 0 to 15 will flow here on this line, while bits from 11 to 15 will flow in this line. So as if it's connections. Okay, and as I stated, at this position in the instruction decode, I do not know what type of instruction I'm executing. Remember, how did we know what type of instruction we are executing? From what? From the opcode. We stated that the opcode, bits 26 to 31, tells me which instruction I am executing, because each instruction has a unique opcode, except for the R format. All R format instructions like add, subtract, or, and AND, for example, all share the same opcode, which is zeros, and thus we have the function field, which is a 6-bit field identifying which instruction inside the R type. The add instruction has a different function bits than the subtract instruction, for example. So I'm not processing the opcode information or the function information in this decode. I'm just dividing the instruction into multiple fields. So it makes sense that at this stage, I do not know which instruction I am executing. Okay? So, as you can see, the instruction decode is divided into 2 parts. The first part is decoding the instruction and dividing it into multiple fields regardless of what format is the instruction, R, I, or J. It will try to force or will try to divide the instruction to all possible formats and all possible divisions, because it does not know which instruction type I am executing. That's the instruction decode. The second part of this stage is the register file read. So I will retrieve the data that I need from the register file. For example, if I am executing an R-type instruction, then I need to retrieve or get the value of the register of RS and the value of the register of RT. So in here I provided the register number of RS and the register number of RT, which are 5 bits. In the register file, I will get the data of both registers, and here in this line I will output the value of RS, and here I will output the value of RT. So regardless, even if I am an R format instruction, it makes sense to get the RS and the RT. But if I am an I format, the RT is called the target register. It is not source 2. It's not acting as if it's source 2. No, it's a target register. I will save my result into the RT. So guess what? Because we're still in the instruction decode stage, it does not know which instruction I am executing, so it will try to retrieve, it will not even try, it will retrieve the value of register RT even if it is an I format instruction. Okay, but guess what? This value will not be used later throughout the data path when the data path processes the opcode and the function, if there is a function, and knows which instruction. But till now, there is no processing for the opcode, so I do not know which instruction I am executing. So guess what? I will always try to get the value of RT regardless of what format I am. If I am an R format, if I am an I format, even if I am a J format, I will always get the value of the RT register. So here we got the value of the RS, here we got the value of the RT, and that's the end of the register file phase, or overall the instruction decode and register file read stage. Let's move on to the third stage, which is the execute an address calculation stage. As you can see, inputs to this stage include what? Include the values I retrieved from the register file from the decode stage. So the main component of the execute stage is the ALU or the arithmetic logic unit. Okay, the arithmetic logic unit performs any arithmetic operation we have. If I'm doing an addition, it is performed inside the ALU. If I'm performing a subtraction, it's performed inside the ALU. So all arithmetic operations are performed inside the ALU, and that's why we call it the execute stage, because I am executing the instruction. It's an addition instruction, I'm performing an addition. It's a subtract instruction, I'm performing the subtraction. Where does it occur? It occurs here in the arithmetic logic unit. And as I stated before, you can find throughout this data path multiple adders. I mean, here there is an adder, here we have an adder. Why do we have multiple adders although we have an arithmetic logic unit? Because I cannot access the same component more than once in one clock cycle. That's why if I want to perform multiple additions throughout the data path to calculate, for example, the program counter or the branch address, I need to perform it outside the ALU. So that's why I add different adders, for example. Okay, you can find here also in the execute stage that it is also called the address calculation stage, because if I'm having a branch on equal instruction like the BEQ instruction, I will calculate the address it must jump to or it wants to jump to in this execute stage. So where is the address calculated? We have here an adder that calculates the address. And as you recall or you remember, the branch on equal and the branch not equal instructions are I format. They are not J format. So they are divided into opcode, RS and RT, the two registers I'm comparing each other with. And then we got the immediate, which it is not called immediate now, from bits from 0 to 15 now are called offset in case of a branch or a branch not equal. That's why we always talk about bits from 0 to 15 as immediate / offset, because it's an immediate in case of an immediate instruction like add immediate, but it's called an offset as if I'm using a branch on equal or a load or a store instruction, because they are not immediates, they are offsets. And as you know, branch instruction, it branches relative to the instruction I'm standing to or I'm pointing to, meaning that I branch relative to the program counter address. The program counter contains an address, and this address I will add or subtract from it a value to jump to the correct destination I want to jump to. And that's why in this adder, one of the input parameters is the PC plus 4. Here I performed the PC plus 4, so this adder takes its first input parameter, the PC plus 4, and the second input parameter are bits from 0 to 15. As you can trace it back, this line we stated that it takes bits 0 to 15 of the instruction. Here it performs something called the sign extend, we will talk about later in this tutorial, and then here it performs shift left by 2. And if you remember shift left by 2, what does it perform? So shift left by 2 corresponds to multiplying the value by 4. Why should I multiply the value given to me by 4? Because the value in the offset field of the branch on equal instruction is in words, meaning that this value, if it is 1, it means you need to jump 1 word. If it is 2, it means you need to jump 2 words. If it is 3, it means you need to jump 3 words. And guess what? We are working with byte addresses. So I need to convert this value that corresponds to how many words I will jump into how many bytes I need to jump. So how many bytes I need to jump? I need to multiply this value by 4. Since 1 word equals 4 bytes, so if I need to jump 3 words, I need to multiply 3 by 4. Okay? So this is the reason I perform the shift left by 2, which is the multiply by 4 operation. Now we will have this result, which takes the PC plus 4, and as I stated, the PC plus 4 is the address of the next instruction, and as you can see, we calculate the branch address or the destination address relative to the next instruction, not relative to the current instruction, because I already I am already executing the current instruction, and the PC is pointing to the next instruction. That's why this input is PC plus 4, or the first input is PC plus 4. The second input is multiplying the offset of the branch equal instruction by 4, which is shifting it left by 2. So I can transform the word offset to a byte offset, and then the result will be output here. So, and I will always, even if the branch is not taken or the branch is taken, I will always compute the destination or the target of my branch instruction. So I will always calculate the target of the branch instruction, whether it will be taken or not taken, I do not care. Always in the execute and address calculation stage, I will have the address in case of a branch ready, okay? Because you can guess or assume how does a branch instruction work. In the arithmetic logic unit, I will take the RS value and the RT value, and I will subtract both values from each other. If the result is 0, it means that I need to branch if it's a branch unequal, okay? If it's a branch unequal and the result of the subtraction is 0, it means both values are equal, so I need to branch. Otherwise, I do not need to branch. And here comes the 0 flag. You can see that this 0 is a 1-bit flag. It's a flag, okay? Indicating that if the 0 flag is 1, it means that the result of the ALU operation was 0, regardless of whether the operation was an addition, was a subtraction, was an ending. If the result of the operation is 0, the 0 flag will be 1, and the 0 flag will be 0 if the result is any value other than 0. So the value greater than 0, the 0 flag will be 0. The value equal 0, the 0 flag will be 1. And this 0 flag is used later to tell me if I'm going to branch or not. But in both scenarios, I will always calculate what? The branch address. Okay? That's something that I will always calculate during the execute and address calculation stage. So we can see here that the output of the execute stage is the ALU results. And this is the main output, I mean. We have different other outputs, but the main output is the ALU result. We can find that the ALU results goes to the fourth stage, which is the memory access stage. And the main component, as you all can see, is the data memory, or as I stated before, the data cache. And this stage is exclusively used for the load and store instructions. If I am having a store instruction, I need to store the data to the data memory. And if I have a load instruction, I need to get the data from the data memory. So you can see that the data memory takes as an input an address. And as you can see, this address is coming from the ALU. Why is it coming from the ALU? If you remember, in the load and store instructions, we add the base address, which is the value of RS, to an offset. So this addition occurs in the ALU, okay? And after doing this addition, I will have the final address that I want to access in the data memory, whether if I'm going to load a value from the data memory or I'm going to store a value to a location in the data memory. Okay, that's the first parameter, which is the address. We have a second optional parameter, which is the write data, which is used in the case of store word. In the case of store word instruction or any store, I mean, guys, if I'm talking about load word and store word, because these are the two famous load and store instructions, but we have other instructions. We have load byte and store byte. Okay, we have different instructions for loading and storing, but the most two famous are load word and store word. So if I say load word or store word, I mean the load family and the store family. Let's return, or let's continue. So this write data is actually the value I want to write to the data memory, which is present in register RT. And if we trace it back this line, we will find that yes, the value from read data 2, which is the value of register RT, is passed directly to the write data in case if I am a store word, and even if I'm not a store word instruction. Remember, the data pass is what is dummy, so it will always pass this value to the data memory. Same goes to the address. I will always have an output called read data. But guess what? I'm not loading, I'm storing. Why should I have read data? Because the data pass is dummy. It does not know what instruction it is performing. Yes, it's the data memory. Guess what? I will read data. I will always read data from what? from the data memory. And because this is a simple implementation, there are actually flags telling the data memory which operation to perform, read or write. As I told you, we cannot read and write at the same clock cycle. It does not make sense. So there are flags which does not appear here on this diagram that actually tells the memory or the data memory which action it should perform. Should it write or should it read? But we will always have a line coming here, even if this line has meaningless data. In case of store word, I'm not going to read, so this line will output meaningless data. But this line is present because we have a dummy data path. That's the memory access stage. Finally, we got the write back stage, and the write back stage writes back to what? To the register file. In the write back stage, this stage, we have only two scenarios. The first scenario is I'm writing back the result of the ALU to one of the registers. If it was an addition instruction or an addition of an immediate instruction, an add I instruction, I will take the result from the ALU and then pass it back and save it in the register file. And that's why you can find here write data in the register file, so I can write the data I operated on or I performed or whatever operation I performed inside the ALU. The result will be stored, will be transferred, in this line, in this blue line, to the write data, and will be stored in which register? The register that is stated in the write register. So the write register has 5 bits that tells me which register you need to store this data in. So write data contains the actual data, and write register contains the number of the register you will store the data in. And the second option, you can store a value in a register, is if you are loading data from the memory. If you are loading data from the memory, then in the read data, you need to pass the value you read and pass it back where? To the register file, to the write data, and the write register will have the register that I need to write or store this value in. So basically, write back is a simple stage. It accesses the register file to just write a value. If it is the result of an ALU operation, as you can see from this line, or if it is the result of a loading from the memory and I need to store it in a register. Now, smart people like you, because I believe you are all smart, will tell me, there is now a problem. We can all see. I am accessing the register file twice. I'm accessing it in the decode stage, and I am accessing it in what? In the write back stage. So if you reach this conclusion, then you are understanding the tutorial. If you did not reach this conclusion, I don't know, but I guess you are understanding some of the tutorial. Okay, so why or how actually we are accessing the register file twice in the same clock cycle? Well, guess what? That's for your general information. So, a register is a group of flip-flops. If you remember flip-flops from your DLD and DSD courses, okay? We can imagine that a flip-flop consists of 3 parts. We have the input part, the store part, and the output part. The input part is the value. If I want to write a new value to a flip-flop, I pass it through the input part. Then we got the store part, which consists of the actual value inside the flip-flop. And finally, we got the output part, which is the value being outputted from the flip-flop. We can imagine that if I want to read a value from a register, I read it from the output part. Okay, this part is asynchronous. It does not need clock synchronization. I can read the value of the flip-flop at any time during any clock cycle, whether it's a high edge, a low edge, a positive, negative edge triggered. I can read it anytime, okay? And the problem is changing the value of the store. The value of the store is actually the value being output. So to have a new value or to write a new value to a flip-flop, I need to pass it in the input so it can change the store value. This mechanism needs to be synchronized, and this is an edge triggered mechanism. Okay, its synchronization or its triggering is when I change the edges from low to high, for example, of the clock. Okay, so here in the write back, let's assume I calculated the new value and now I want to store it to the register file. Guess what? If I'm in clock cycle 1, I'm performing this instruction in clock cycle 1, the value will not be actually written in clock cycle 1. we assume it's written in clock cycle 1. Okay, we assume it's written in clock cycle 1. But what actually happens in the hardware is that this value is standing in the input part of the flip-flop. It did not enter. The input part is like a door, okay, and it did not enter the store part of the flip-flop. So in the next edge trigger, when I start clock cycle 2, before I do anything inside the data path, the input door will be open and the value will change. The store value will change. The flip-flop value will change and it will be reflected in the output value. So the value standing at the door outside will enter on the next edge triggered of the clock. Okay? So this will be reflected, as I stated, in the output. So when I perform the next instruction, I will have the updated values. And as I stated, reading from a register is asynchronous. I can always read from a register. It does not need any clock synchronization. So guess what? I will read normally the new value, because the new value is already in the store state, and the output state or the output part outputs the value present in where? In the store state. That's it. So actually, physically, I'm not accessing the register file twice at the same clock cycle. I'm only accessing it once in a clock cycle, because the write operation is the only operation that needs synchronization with the clock, while the read operation does not need any synchronization with the clock. But take care, I can read two registers simultaneously due to this fact. So that's why if I want to read two registers simultaneously, I will provide two inputs to the register file. If I want to read three registers simultaneously, I will provide how many input? 3 inputs. Because as I stated, reading from registers is what? Asynchronous. But I can only write one value per clock cycle. That's why we can only write what? One value per clock cycle. Due to the synchronization, that writing to a register needs synchronization with the clock, while reading from a register does not need any synchronization. So it's technically I'm only accessing the register file once for writing, because reading from flip-flops or registers is always asynchronous. Okay, this is general information. We will not tackle it in the exams or just in details. It is just for you to understand why we have an instruction decode and a write back, both accessing the same component, which is the register file, although we stated that we can only access a component one time per clock cycle. And even if you can see here, no one commented about, you can't comment, but yeah, no one commented about that we can have two inputs to the register file. So this means I can read the value twice, or I can read two different values from the same component. Yes, because it's asynchronous, and I can have 3 read registers. I can have 4 read registers. It depends on your implementation, because the read is always asynchronous. The only synchronized action, which is an edge triggered action, is the write. Okay, that was the 5 stages of our data path: instruction fetch, instruction decode, execute, memory, and write back. IF, ID, EX, MEM, and WB. This is a simple implementation. As I stated, we will extend this implementation throughout our tutorials and lectures. Now let's move on practical examples and start our problems of the tutorial or the practice assignment. So now let's move on to some practical examples. The first example is an R format instruction example. We have here add T1, S1, and S2. We are adding the values of S1 and S2 and storing them in T1. As you recall, the R-type instruction is divided into an opcode, which consists of 6 bits, an RS, which consists of 5 bits, RT, which consists of 5 bits, RD, which consists of 5 bits, shift amount, or SA, which consists of 5 bits, and finally the function, which consists of 6 bits. We stated before that the opcode uniquely identifies the instruction. So to differentiate between different instructions, we use the opcode. And as you can recall, we stated that the R format instructions all share the same opcode. They all share the same opcode, which is 0. So we have the function field to uniquely identify which R format instruction we are talking about. So for example, the add instruction will have an opcode of 0, the sub instruction will have an opcode of 0, but there will be, or they will have different function bits. So now we need to translate this assembly instruction into machine code or its equivalent binary representation. Okay, so we can trace it in the data path. The first thing we need to do is identify the key elements here. So T1 register is the destination register, which is RD. S1 register is the source register or the first source register, which is RS. S2 here is the second source register, which is RT. So first of all, we have the opcode, and as I stated before, all R format instructions have an opcode of 0, so the opcode will be 0 in decimal, which is if we want to translate it into binary, and this field takes 6 bits, so we will write 6 zeros. So now after getting the opcode, we need to get the function. Okay, and only the R-type instructions have functions because they share all the same opcode, so we cannot use the opcode to distinguish between the different R format instructions. So we have the function which are 6 bits. You will be provided in the exam with a list of the R-type instructions and equivalent to each instruction its function, or the function of each R-type instruction. So you will retrieve the function of the add from this table. You will find out that the function of the add is 32. So I need to convert 32 into binary, which is 1 and 5 zeros, because the field is 6 bits, so it will be 1 and 5 zeros. Okay, now we have the opcode and the function. We need to get the rest of the fields values. So the RS is S1, the RT is S2, and the RD is T1. These registers have numbers, so we need to know S1 is equivalent to which register or to which number, S2 is equivalent to which number, and T1 is equivalent to which number. Since we have 32 registers, so we need 5 bits to represent all 32 registers, and that's why the fields of RS, RT, and RD take each 5 bits. So we can represent the entire register file or our entire 32-bit registers. So we will have this table having our 32 registers and their equivalent numbers. So for example, T0 is register number 8, T1 is the register number 9, T2 is the register number 10, etc. So since our code consists of saved registers and temporary registers, we will focus on these numbers. So we are using S1, S2, and T1. T1 will be 9, S1 will be 17, and S2 will be 18. So if you want to get register S1, as we stated, S1 will be what? 17. Why 17? Because S0 is 16. So it's tedious. S1 will be what? 17, because it's in order. Okay? So we'll find out that RS is equal to register S1, which is 17. 17 in binary is 10001, which fits in 5 bits. Now we need to get RT, which is what? 18, which is in binary is 10010. So RS is S1, which is register number 17. RT is S2, which is register number 18, and these are their equivalent binary representations. Okay, now we need to get what? The RD, which is T1, which is register number 9, 01001. Take care, if you translate or transform or convert number 9 from decimal to binary, you will have it on your calculator as 1001. But since this field takes 5 bits, we need to add a 0 at the beginning as the most significant bit. So I cannot just leave it 1001. No, you need to represent it in 5 bits. So if you want to represent it in 5 bits, you will add what? Zeros to the left. Okay? And finally, we got what? We got the shift amount, and as you cannot see definitely because the menu's option, yeah, now we can see the shift amount is 0, and since the shift is 5 bits, so we need to convert the 0 from decimal into binary, so we write 5 zeros because the field is 5 bits. And why do we use the shift amount in general? Because there are instructions like SLL, shift left logical, and SRL, shift right logical, where they take an immediate or the amount to be shifted. So I need to shift the amount inside a register by, for example, 2 to the left or 3 to the right. So this number is written in the shift amount. And take care, shift left logical and shift right logical are R-type format. They are not I-type format. That's why if you check the formatting of the R-types, we do not have any fields for what? For the immediates. And that's why we have a field for the shift amount exclusively. Okay, so this field is 5 bits, and for example, if I want to shift to the left by 2, I will write in this field 2, and 2 in binary is what? Is 1, 0, but since it takes 5 bits, so I will write 0, 0, 0, 1, 0. Okay, now we converted the instruction and we decoded it. Okay, this is the decode. Can you see these divisions? That's what the data path does. It divides the instruction and passes it to the equivalent components in the data path. This is just a summary of the previous example and how did we divide the instruction and transfer it or transform it from its assembly to the equivalent machine code. As you can see, we have here the opcode, which is zeros, identifying that it's an R-type, and we here have the function 1 and 5 zeros, stating that it's an add instruction. Then the RS is 10001, which is S1. The RT is 10010, which is S2. The RD is 01001, which is T1. And finally, the shift amount is 5 zeros, which is 0. Then these values are concatenated together to perform or to have a 32-bit instruction. Let's start our data path history or journey. Okay, this is the data path journey. First of all, as you can see on top of the screen, this is the instruction after we transferred or transformed it from assembly into machine code. The first thing that comes to you is what? Yes, the program counter. The program counter or the PC contains the address of the instruction I want to execute, which will be which instruction? This one. So this value, as you can see it, will be stored in the instruction memory at address that is stored in the PC. So in the instruction fetch, which is the first stage, I will do what? I will fetch the instruction from the instruction memory. Okay, I will get this value from the instruction memory. And this is what stage? This is the instruction fetch stage. Okay, then what we will do, we will move to the instruction decode stage. As you can see here, as I told you before, the lines here contain some bits of the instruction. So in the decode, I decode the instruction, meaning I divide it into multiple fields. For example here, instruction from 21 to 25. This means what? The RS. So on this line, what value will be moving? 10001. It's the RS from 21 to 25. Then this line is called from 16 to 20, which is the RT, which is 10010. So this value will be moving onto this line. The read register 1 and the read register 2 are the RS and the RT. So I want to retrieve their values from where? The register file. As you can see here, we got what? We got instruction from 11 to 15. 11 to 15 is the RD, which is 01001. So on this line, we will have this value 01001 moving. Okay, and finally, the decode will end here, which is having the instruction from 0 to 15, which is 0. It is here till 15 here. So it contains the functions, the SA and the RD. And as we stated, the data path is dummy. It does not know what type of instruction we are executing. It does not know that it's an R type or an I type or a J type. Okay, so it assumes it will decode into all three possible formats. So this is in case it was an I instruction. But we know that it's an R type, so we will actually put the value from 0 to 15 here, but we know that further on in the data path we will not use this value. Okay, now one important thing I did not talk about, which is the multiplexers present. We have multiple multiplexers or muxes present. What is the functionality or the role of these multiplexers? They act as a gate, meaning that they choose one of the two values entering to pass. So basically it will have an input, two values, and it will decide one of these two values will pass to the next stage. How do we choose which value to pass to the next stage? We have something called the control unit, which passes multiple signals to these muxes. the signals are created from the opcode. So the control unit has an input, the opcode, and then according to this opcode, it will set or clear the signals of the multiplexers. So if I am a R-type instruction, which register will I write my data? Will I write my data in the register specified from bits 11 to 15, 11 to 15, which is the RD, or I will write my data in the register specified from bits 16 to 20, which is the RT. If I'm an R-type, do you think I will write my destination will be RT or RD? Definitely it's RD. Thus the multiplexer signal, the regdest will be 1, and this value will pass here. So the right register will be the value from 11 to 15 and not from 16 to 20. So why do we have a multiplexer here that we can choose between these two values? Because if you remember in the I format instructions, if I am using an add immediate instruction, the destination register is RT. RD does not exist in the I format. So this multiplexer will know that I am on I format, I'm on I format, and thus will choose the RT and not the RD, or technically it will choose bits from 16 to 20 and not from 11 to 15, because in case of an I format, bits from 11 to 15 are useless. They do not mean anything. They do not represent any information about the instruction. They are actually part of the immediate, so they are useless in I format. Okay, so as I told you, the data path is dummy. It does not know what instruction it is executing, so it's trying to process or create all possible combinations or divisions. That's why there are two options for the right register. Either it's RT if I am an I format, or RD if I'm an R format. Okay, so let's continue. We will have these values as I stated before, and as you can see, it took the entire values from 0 to 15, although it's an R type, but it does not know, so it will take the value. It's dummy data path. And then here in the register file, I will get the data inside this register, and I will get the data inside this register, and output them here. So here we'll have the value of RS, and here we'll have the value of what? RT. Okay, and this is the instruction decode phase or stage. Moving on to the ALU, after getting the values of RS and RT, I will add them here in the ALU. As you can see that the RS is always an option to the ALU, so the value of RS will always enter to the ALU, and then here I have a selection mux. As I stated, muxes are gates. They allow only one value from the two values to pass. Which value will pass according to what? To the control signals, which is triggered or are triggered by the control unit. And how does the control unit know which signal to trigger? According to the opcode. Since the opcode tells the control unit, yes, I'm executing an R format instruction, an I format instruction, a J format instruction, so I need to pass only the relevant data, the relevant divisions the decode stage made, not all the divisions the decode stage made. Okay? So here we are choosing either between the value of the data of RT or the value of the immediate. Okay, so if you are an R format, you will always select what? The value of RT. But if you are an I format, like an add immediate instruction, what will you do? You will pass the value of the immediate, because I do not care about the value of the RT, because actually the RT is my destination register in that case. It's not a source, so I do not care retrieving its value. Yes, its value will be retrieved because we are in a dummy data path, but guess what? The control signals are the key. They choose what to pass, and this is implemented through what? The multiplexers or the muxes. So in our case, we are an R-type format, so the ALU will take the value of RS, and the ALU will take also the value of RT. This mux will pass the value of RT and not pass this value, because bits from 0 to 15 are meaningless in R-type formats, so I do not need to pass them here. And then we perform what? The addition operation. How do we know the addition operation? We have something called the ALU control. The ALU control tells the ALU which operation to perform, and we will talk about the ALU control later, but for now you need to know that the ALU will tell the ALU, okay, perform an addition instruction, perform a subtraction instruction. Okay, it's like it's selecting which action or which arithmetic operation it will perform. Great, that's the execution stage. Now we'll go back to the write back stage. As you can see, we did not enter the memory stage, although technically speaking the bits will pass. I mean, we will have here the result of the ALU, and after having the result of the ALU, it will pass to the data memory as an address, and at the same time it will pass to this multiplexer. Okay, and according to this control signal, it will select either the direct output of the ALU or the data coming from the data memory. We are an R-type instruction. Guess which data will pass from the data memory or from directly from the ALU? As you guessed correctly, I hope, the data from the ALU. But as I am repeating for the millionth time, the data path is dummy. It does not know exactly what instruction you are performing. Yes, I got a result from the ALU. Guess what? I will pass it directly to this multiplexer, and at the same time I will try to retrieve data, I will try to get data, I do not know, but I will pass it to the next stage, which is the memory stage. But I am not a load or a store instruction, so I will not use the memory, but the data is automatically passed to the next stage regardless of the instruction type. It's very important, I know. Okay, so this multiplexer will select directly the data from the ALU, and then it will pass it back to the register file. After passing it to the register file, why do we pass it to the register file? Because we are executing the fifth stage, which is the write back stage. So I'm writing back to the register file, which is the RD. That's why in the write register we chose the destination to be the RD bits from 11 to 15, and write data here will have the data coming from this multiplexer, which is the data got directly from the ALU. Okay, so it's simple. I know it's very complicated at the beginning, but if you practice a lot, you will find it simple. So recapping quickly, the program counter contains the instruction or the address of the instruction I want to execute, which is this instruction. It points to it. So in the instruction fetch, I will retrieve this instruction in this format, 32 bits concatenated. In the instruction decode, the second stage, I will divide the bits to multiple fields regardless of its type. I will try all different combinations. So here I took bits from 21 to 25, which were the RS. Here I took bits from 16 to 20, which are the RT, bits from 11 to 15, which were the RD, and bits from 0 to 15, which were meaningless in the terms of R format, but they exist, which consist of the function, the shift amount, and the RD. Okay, then in the decode, the second part, which is the register file read, I will here read the value of register RS and output it here, and then here I will read the value of register RT and output its value here regardless of its type again. And here I do not know the write register, so using this multiplexer I need to pass one of these two values, because if I'm an I format, I will pass the RT because it will be in that case the destination register. If I'm an R format, I will pass the RD because at that case it will be the destination register. Okay, but we care about this in the write back. So this occurs in the write back. So someone smart will tell me, yes, in the decode it does not know actually the instruction. So how do we have here a multiplexer with a control signal if at the decode we do not know the instruction? Because I will write in the fifth stage, the write back. So this signal is triggered in the fifth stage. So actually we have the control unit getting out or releasing its control signals depending on the opcode, and thus this multiplexer will have its correct signal. Okay, so this step, this multiplexer does not occur in the decode, it occurs in the write back. Okay, after getting here the values, I will have the value of the RS input to the ALU, which is the third stage, the execution stage. And here the second parameter to the ALU, I need to know the data, whether I'm taking the value of RT or I'm taking the immediate value bits from 0 to 15 directly. And we will talk about the sign extend later on. Do not worry. Okay? So if in our case we are an R-type instruction, we will definitely take the value of RT, which is read data to, and not the value of what? The immediate, because we do not have an immediate. The value of this is meaningless. This is not a number. This is not an immediate number. It's just a bunch of bits concatenated. Okay? Then after getting the ALU or performing the operation, how can I perform the operation? The ALU control tells the ALU which operation to perform, and we will perform in that case the add operation. So the ALU control will tell the ALU perform an add operation. After we perform the add operation, we will have the result going into two fields. The first one will go directly to this multiplexer, and the second one will go to the data memory, which is the fourth stage, the memory stage. If we are not a load or a store instruction, then we will not do something to the memory, but it will have an automatic input, an automatic address from the ALU, because it's a dummy data path. So this multiplexer will choose the correct data and definitely will choose the direct output from the ALU, and then we move on. This is the fifth stage, the write back stage. So we'll move on back to the register file to write our data. In that case, we will choose from this multiplexer one of our write registers. We will choose what? The RD, because we are an R type. If we were an I type, we will choose the RT. If we are an R, we will choose the RD. And since we are performing a normal addition, which is an R type instruction, we will select what? RD. And here write data will have our data, the actual data, write register containing which register I want to write my data to. And then we finished execution of this instruction in one clock cycle. Till now, we finished the execution of the main elements in the data path, but there are sub-elements, like for example, the program counter, which is the PC. We stated before that we need, after each clock cycle or in the clock cycle, after fetching an instruction, we need to update the program counter to point to the next or following instruction, and we updated with what? +4. So yes, this adder is done simultaneously with the fetching of the instruction. So at the same time I'm fetching an instruction from the instruction memory, I am updating the program counter PC +4. Okay, and as you can see, the PC +4 will enter to where? To two locations. The first location is this adder, and as we stated before, this adder is for the branch calculation. So I need to add the branch offset to the PC +4 to know my target. Where will I go if I will branch? And at the same time, you can see this arrow that the PC +4 is going directly to this multiplexer. Why is it going directly to this multiplexer? Because this multiplexer contains the signal that would tell me whether I will update the PC with this value, PC +4, or I will update it with this value, which is the branch address or the target or destination address if the branch is taken. So this signal depends on whether the branch is taken or not. If it is not taken, I will update my PC with PC +4. If it is taken, I will update my PC with the branch address that I calculated here by multiplying my word offset by 4 to create a byte offset and then adding it to PC +4. Okay, that's the first thing. The second thing, that the ALU control, if you can see, it takes the instruction from 0 to 5 to determine which ALU operation I can take. I did not mention it because I wanted to leave it at the end. As you can see, instruction from 0 to 5 is being retrieved from this line. This line contains the instruction from 0 to 15. I will take a portion of this data, which is 0 to 5, which, if you can recall, the instruction from 0 to 5 contains the function. So if you are an R-type format, bits from 0 to 5 correspond to the function. So I am taking the function bits, the 6 bits, as an input to the ALU control. Okay, so if the ALU operation determines that our instruction is an R-type instruction, then using these 6 bits, I will determine what bits I should output to the ALU. And what bits should I output to the ALU? These determine what operation the ALU will perform. We will know later on that the I format and the J format and the R format will provide the ALU with the operation it should perform through the ALU control. But since the R type contains multiple operations, so it cannot directly state, yes, it's an R, so I will going to perform this operation. No, using the opcode or knowing that it's an R type format, I need to get the function and then perform the operation, whether it's an addition or a subtraction or an ORing, etc. So the ALU control has a control signal from the control unit stating you are executing whether a load or store instruction, whether a branch instruction, or whether an R-type instruction. And since the control unit, which is not visualized here in this diagram, but the control unit takes as an input the opcode and outputs the corresponding signals, and the R-type format all shares the same opcode, which is 0. So from the opcode alone, I cannot know which R-type instruction, and that's why the ALU control, in case of an R-type instruction, it will have as an input the bits from 0 to 5, which are the function bits, plus the ALU operation signal, which is from the control unit telling you, yes, it's an R-type format, and since it's an R-type format, you need to look into the function bits from 0 to 5. But if it was any other instruction, not an R-type instruction, then it will tell the ALU control ignore bits from 0 to 6, from 0 to 5, I mean. So bits from 0 to 5 are ignored if the ALU operation, this signal I'm pointing to, does not state that I am an R-type. If it states that I'm R-type, then I will take it into consideration. And here this line outputs to the ALU, informing the ALU which operation you should perform, whether it's an addition, a subtraction, or an ORing, for example. Okay, and we will take it in details later. But I wanted to tell you how does the ALU control operates. It has two main signals. This is coming directly from the control unit, telling it which instruction did the control unit know from the opcode. And in case it's an R-type format, I need to have the function bits. That's why it's an input to the ALU control. Okay, finally, the last element we did not take in our simple implementation was the sign extend. It takes the 16-bit immediate and outputs a 32-bit immediate. And a sign extend is not like a zero extend. A sign extend extends the number according to its sign, so it's used for signed numbers. And zero extend just extends the number with zeros, assuming it is unsigned. So sign extend means our number is signed, so this immediate value is signed, it's a signed number, and thus if it's a negative number, I need to extend it from 16 bits to 32 bits. So I will look into the sign bit, which is bit number 15, the most significant bit. Bit number 15 is the sign bit. If it is 0, I will add 16 zeros to the left. If it is 1, I will add 16 ones to the left. 0 means positive, 1 means negative. So I'm checking on the sign bit, which is bit 15, the most significant bit. If I find it's a negative, meaning it's 1, I will add to the left 16 ones. And if it was a positive number, meaning this bit is 0, I will add 16 zeros to the left. Okay, and that's how sign number works, or sign extend works. Why do I extend a 16-bit number to a 32-bit number? To preserve the alignment, meaning all data present in the data path are 32 bits. I cannot just, for example, add a 32-bit number to a 16-bit number. Okay, I need to make this 16-bit number aligned with the 32-bit number. So how to align a 16-bit number? I need to extend it to be a 32-bit number. And that's why we use the sign extend, to extend 16, for example, to extend any bits. But here we extend 16 bits to 32 bits, so we can preserve the alignment of bits. As I stated, we have our data in 32 bits, and the data path and the hardware does not support incompatible types. I cannot just say, or incompatible widths. It's like an incompatible widths. I cannot add, for example, a 32-bit number to a 16-bit number. The ALU will not work. It will refuse. Okay? And that's the reason of the sign extend, and we will talk about the sign extend in details later. Now I am done with part 1, where I explained the MIPS data path single cycle implementation, as well as taking an example of an R format instruction passing through the different data path stages. In the next video, which is part 2, we will see the execution of 3i format instructions, the add immediate, the load word, and the store word, passing through the different data path stages, as well as solving exercises 2 and 3 from practice assignment 7. So see you in the next video.